Hello everyone, welcome to Nrcm. This is Shravani and I'm going to explain about operating system subject of Unit 3 and the topics are monitors and IPC mechanism. So first of all, the monitor is one of the ways to achieve the process synchronization. And the monitor is supported by the programming languages to achieve the mutual exclusion between the processes. For example, like some Java synchronized methods, like Java provides like wait and notify you notify type of the methods. So it is a collection of the condition variables and procedures combined together in a special kind of module or a package. So actually, and these monitors are their high level abstraction, their high level abstractions. They will provide the convenience and effective mechanism for process synchronization. So if you want the convenient and effective mechanisms for any of the synchronization, then we can go for the monitors. So here at the monitor, like only one process will be active within the monitor at a time. So if the process is entering into the monitor, so only one process will be active. So and here comes the syntax, like this is the monitor and monitor name. So this is the monitor name, is name of the monitor we can give. Here we can declare the variables which can be of, like variables can be shared variables or condition variables also. So the variables can be shared or condition variables. And if you want to give, like you can give number of procedures like procedure 1 to procedure n, and then you can mention the code, and then and this is the syntax of the monitors. And next is, what are these condition variables? These condition, as I discussed, like here you can give any kind of the variables. So these condition variables are like two different operations are performed on these condition variables. So first one is wait and second one is signal. So in wait operation, what happens? So the process will perform the wait operation on any condition variable are suspended. The suspended processes are placed in the block queue of that condition variable. So and here each condition variable has its own unique block queue. And next is signal operation. So when a process performs a signal operations on any of the condition variable, one of the blocked process is given the chance. Like I wanted to show here the next slide. So here are the condition variables. So first one is wait. So as I discussed, so if any of the like process performing any wait operation on any of the condition variable, and they will be, that processes will be suspended, and the suspended process are placed in the block queue. In the suspended places, they are placed in the block queue. Okay, next coming to the signal operation. So if when the process performs the signal operation on condition variable, one of the blocked process is given chance. Means here the for the blocked process it will be giving the chance, and here waiting. So whichever the process are waiting, they will be in blocked state. So if any of the, if any of the process are in the blocked states or block queue, so the signals will be ignored, else it will resume the process from the block queue. And here I just want to give the advantages of monitor. So I feel that like monitors have the advantage of making parallel programming easier and less error prone than using techniques such as the semaphore. And there, like the disadvantage is like monitors have to be implemented as a part of the programming language. So that is the disadvantage of the monitor. So next I'm going with the topic interprocess communication mechanism. So in IPC mechanism, so we have pipes and FIFOs. So here a pipe is a mechanism for interprocess communication. So here data written to the pipe by one process can be read by the another process, and the data is handled in a first in first out order. And this pipe has no name, and here the pipe has no name, and it is created for one use, and both ends must be inherited from the single process which creates the pipe. And next, a pipe or FIFO, or you can say like a pipe or, like coming to the next, this FIFO, it is a special file. So it is a pipe is mechanism for interprocess communication. Coming to the FIFO, it is a special file which is similar to the pipe, but here what happens, but So here what happens, temporary connection, this FIFO is the temporary connection, so it has a name. So here pipe doesn't have name, but it has a name. Okay, it has a name like any other file. So processes open the FIFO by name in order to communicate through it. So if any of the process want to communicate through it, it opens it by the name. The process will be opened by the through the name. So here, but a pipe or FIFO has to be opened at the both ends simultaneously. If you read from a pipe or a FIFO file that doesn't have any processes writing to it, so then the read returns end of a file. So this will return the end of a file. Writing a pipe or FIFO that doesn't have a reading process, and it is treated as an error condition, and it generates a signal and fails with error code, and if the signal is handled or blocked. Okay, and next, but coming to this, neither pipes or FIFO special files allow the file positioning. So both reading and writing operations happen sequentially here. So reading from the beginning of the file and writing at the end of the file. So first what happens, it creates a pipe, making like it makes a pipe with a pipe function. Okay, pipe and pipe to a sub process, using a pipe to communicate with a child process. And FIFO, what it will do, it will use the special files and making this FIFO as a special file, and like it is like we call it as pipe automaticity when, sorry, pipe atomicity when the pipe or FIFO is automatic. Whether it is single, then we'll be calling it as pipe atomicity. Next, I'm going to explain about this shared memory. So we all know that shared memory, like inter-process communication through shared memory, it is a concept like where more than one process can access the same memory or common memory, and communication is done via this shared memory. So, and where the changes made by one process can be viewed by the another process. But the problem with pipes, FIFOs and message queues is that for two processes to exchange the information has to go through the kernel. So what happens here, first of all, server reads from the input file. The server writes this data in a message using either pipe, FIFO, or a message queue. Then the client reads the data from the IPC channel, again requiring the data to be copied from kernel's IPC buffer to the client's buffer. Finally, the data is copied from the client's buffer. So a total of 4 copies of data are required. So 2 to read, 4 write, 2 to read, and 2 to write. So here shared memory provides a way by letting 2 or more processes, they can share memory segment with shared memory. The data is only copied twice, from the input file to shared memory and from shared memory to the output file. And here this shared memory, it can use the different system calls also. The first, like it can use fork system call, and it can use like different system calls like fork, as you all know that it is used for creating, and upon successful completion it can use like shmget system call, shmat. Like this shmat is used before, and this is used before the shared memory segment. Okay, and different kinds of system calls can be used by this shared memory. So next, coming to this message queue. Next, discussing about the message queue. So the message queue, it is linked list of message and stored, it is a linked list and it is stored within the kernel, and it is identified by the message queuer. So here what happens, a new queue is created, or if already queue is present, so for the existing queue, so a message, if there is a queue is already existing, so that queue can be used. So, and for that already existing or created queue, so new messages are to be added to the end of the queue. So if you want to get the queue, you can use the command called as a message get, and if you want to add any of the messages, you can add it at the message, you can add it msg end. So here every message, it has a positive long integer type field. So the message format will be like, so it will be having positive integer type field and a non-negative length, and the what is the actual data, like it will be present in the bytes. It will be what is the actual length of the data, that will be in bytes, and some message, and it will be attached with some of the specified messages. So when the message is added to a queue, messages are fetched from the queue by MSG RCV. So with the help of this function, the messages are fetched from the queue. You don't have to fetch the messages in a first in first out order. Instead, we can fetch the messages based on their type field. Based on the type field we can. And here what happens, all the processors, so in the shared memory, like all the processors, they can exchange information through a common system, that is through message queue they can access. The sending process, first what it will do, it places the message, into the queue, which can be read by the other process. And next, each message is given to the each message, different message, it has given different identification or the type, so that the process can select the appropriate message. So it will select its message, and next process will be shared, and process must share a common key in order to gain access to the queue in the first place. So here, so this is all about the message queue. And some, this message queue also, it uses some system calls, different system calls, like as we has I have showed in the screen. Like normally first fork is used, it can generate a unique key. Next, msg get, as it is there here, it is there msg get. So this is also a system call. So it returns the message queue identifier or newly created messages. And msg snd, so here data is placed onto a message queue by calling it. Data is placed. And next, msg rcv, so this is also a command, the system call. So it messages here, with the help of this function or system call, messages are retrieved from the queue. Okay. And msg end, this is same, this is the same like the system call. Okay, this is all about the shared memory and message queue. Thank you.